Hello everyone, my name is John Rodman. This is my DFMA review of the Nutcracker. In this presentation, we'll start with an introduction, some background information on the Nutcracker, future state recommendations, questions I might have for the client, summary of the changes that we've made and the benefits of those changes, and some references. In this project, we were asked to apply DFMA criteria to the Nutcracker in its current state. The reason being is we want to make the design more suitable to assemble and manufacture. In this process, we want to also achieve a 50% overall cost reduction by critiquing design parameters, material selection, the implications for assembly, and the proposed manufacturing methods. Regarding specifications from the client, they're looking for a table-mounted device with a capacity of 80 to 100 nuts per minute. If we look over here at figure 1, we can get an idea for the operation. The nuts drop in through the top and nest in the grooves on a turning wheel. This wheel drags the nuts over, presses them against the crusher, where they crack and fall out through the bottom. The design needs to be made from food-grade materials that are corrosion resistant, and in terms of technical specifications, they're looking for tolerances of 2 thousandths unless otherwise stated, 16 micro-inch surface finish, and compliance with GMA guidelines. The client also specified what they were looking for in terms of production volume and the life cycle of this product. So if we look at the graph a little bit, we see that in the first year, they're looking to produce roughly 3,600 units. Year 2, 9,600 units, where year 3 comes in at 21,600 units, and then is produced at that quantity for the rest of the expected life cycle. So we look at years 8, 9, and 10, and those are the expected drop-off years for the life cycle of this piece of equipment. So in total, we could produce anywhere from 142,000 to roughly 186,000 of these units over the product life cycle. So looking at the manufactured and purchased parts suggested by the manufacturer, we see that there's 6 manufactured parts and 4 purchased parts. With the manufactured parts, they all are recommended from 304 stainless steel. And when we take a look over here at the material and outsourcing costs, we see that they're relatively high, and that's reflected in the material cost per component. The write and return side are significantly higher than the rest, roughly 3/4 of the cost of the material in one Nutcracker that comes in just under $4,000. Purchased parts is relatively low in comparison at $54.16. So this leads to a total part count of 19 and a material cost per unit with outsourcing that's exceeding $4,000. The next thing I'd like to bring attention to is the current supply chain for the current state model. If we take a look at each separate component over here that's being produced, we realize that in the supply chain, every single manufactured component goes all the way through tertiary processing. So ultimately, for DFMA, we want to minimize that and eliminate as many secondary and tertiary processes as possible. So this is going to be one area where we hope to make some improvements, is to really simplify the supply chain of this entire design. So over here, we look at the cycle times with the work in process included, and we see that it's going to amount to just about 500 hours collectively for each manufactured unit that goes into one separate Nutcracker. So next up, we'll discuss the machining time per component. One thing that I noticed was that there's not exactly complete information regarding the parasitic time on this model. So that's something that I want to talk a little bit more with the client about. So the costs for machining time are strictly when the machine is actually in a cutting process, and the cost was determined based off the labor rate on that. Overall, we end up per unit with a cost of $63.33 in machining time, with the bulk of that coming from the grinding processes. In terms of parasitic time, we look at the work in process, and that really is the bulk of the cycle time. We see that it really doesn't differ much when we add in the machining and finishing, orienting, loading, unloading, and the tool changes. So that's someplace we can serve to drop a big amount of time on production. The biggest issue I see with the current design is that it has an outsourcing and material cost that adds to more than $4,000 per unit. That's just something that I think we can easily work down, and it's really going to push us to our DFMA goal. Grinding processes are accounting for about 50% of the machine labor costs. There's significant amounts of waste being produced during the processing. Final product is unnecessarily bulky in my mind, which concerns me with the weight with some materials. For example, if we were looking at 304 stainless steel, the design would be well over 50 kilograms. And lastly, the requested general tolerances and surface finish are driving up production costs. So our first recommendation comes in the form of material selection. We looked at other food safe materials, and most 300 grade materials of stainless steel are considered food safe by the NSF, as long as they have more than 16% chromium. We also found that acetyl holopolymers can be considered food safe in most cases, and that particularly Delrin food grade 400 MTD is a metal detectable food safe acetyl plastic. So we looked down here at a comparison of the two. I didn't find a direct comparison, but it seemed pretty clear that 304 stainless steel is difficult to machine, while Delrin is relatively easy. The next piece to mention is the density. Delrin's going to be roughly 1/6 the weight of stainless steel, which is desirable based on the issues we identified, and it's going to be more than 50% cheaper than any form of stainless steel that we're already working with. And I just found those price per pound based on the stock forms that were recommended. Next, we'll talk about our strategy for assembly simplification. We consolidated parts by DFA methodologies, replaced fasteners with snap fittings, and simplified and modularized the casing components. So if we take a look here at the originally proposed right side and crusher, we see that it takes 4 components for that part. So what we did was we flattened the crusher and expanded that wall out a little bit. We also cut off the overhang because it added material and weight without affecting function very much from what we could tell. We also added some snap fittings instead of the through holes for the fasteners that were being recommended. You'll notice that on the left side there have been some holes added. This is because we're going to replace the top plate and the return side with this same component that's just going to fit in a rotated fashion. So if we look at what the assembly is going to look like, it ends up stacking out somewhat like this. So we end up minimizing the amount of tooling that's going to be required, screwdrivers and wrenches. We've reduced the number of parts from 19 to 6. The design is simpler to assemble at this point. It's going to reduce the weight also and simplify the geometry. I'm also going to suggest some significant changes to the manufacturing strategy. Since we'll be selecting Delrin, we can injection mold that to create the casing as well as the wheel. Injection molding is going to be much more economical in the order of thousands to millions of units, and that definitely falls within how many units the product life cycle demands. So injection molding can also achieve the desired surface finish, will reduce the amount of material waste, cut the cost of tooling, and then also cut down on machine labor. So I went to emold.net. This is a Chinese company that produces injection molds and will offer quick quotes. So just based off of the design and a few generalized variables, we were able to get an injection molding quote of $7.23 per casing component and a cost of $4.86 per wheel when we're producing in the numbers that we're looking to produce. When we estimate the savings based on the areas that we took a look at and made some pricing for, we can see that with the suggestions that we made, the manufacturing cost comes down significantly, and that's going to be the bulk of our savings. We end up with a total of 4 units that are manufactured, or 4 parts per unit, and that comes to a cost of only $43.64. Granted, this is a pretty rough estimate. The fact that we're down into 2 figures of magnitude here, it's huge in comparison to the value of the current state's material cost. we look at purchase components, we were able to cut that down pretty significantly as well. And then also on machining expenses, we brought that down almost to 1/8 of the previous cost. So altogether, we go from $4,076.13 per unit to about $81.43 per unit. So that gives us an overall savings of 98% from the current state. So another big improvement was made in the supply chain complexity based on our recommendations. With the recommendations, we end up with only one component that goes through any form of secondary or tertiary processing, and that's the drive shaft. And that's just because we left that alone. We didn't make any major changes to it. But with the housing and the wheel, all we really need to do now is inspect those when they come in and then move them to assembly. So based off of the figures that I received in the process sheets, I estimated inspection and the move to assembly to take roughly 8 hours apiece, giving us an estimate of about 16 hours for each of those components after we received the materials from the supplier. So overall, we've dropped the combined cycle time in the current state from about 500 hours down to an estimated 55 hours, which is a pretty significant drop. So to summarize the recommendations, we're hoping to change the major material from 304 stainless steel to food grade Delrin. And additionally, we want to combine the crusher, covers, right side, left side into a modular 2-piece snap fit housing. Lastly, we want to injection mold the wheel and casing components. In terms of a monetary cost, we're looking at roughly $46 million saved yearly in raw material expense, an additional rough $20 million per year reduction in outsourcing fees, as well as $840,000 per year reduction in specialized finishing labor costs. So if you're more interested in that, you can take a closer look. About the only cost to all this is that Delrin's going to be a less durable material than steel. So there's a chance that it could break over time or wear over time. But with the significant reduction that we had in unit price, it would be relatively cheap to replace that unit as well. So to conclude, just a couple of questions that I had. I was looking to get a little more information on your machines and models. That way we can look a little bit closer at the tooling costs and how that's going to affect the production. And then next, we were looking to get a little bit more detail about what you were considering for mounting, feeding, and driving hardware on the design. We didn't see much in terms of geometry that would allude to these features. So third, does the form factor need to remain as big as it is for any reason? If we could cut that size down, we'll minimize weight and material. Lastly, to what extent can non-critical tolerances be loosened? So here's the list of references if you'd like to take a look. Thank you for tuning in.